Hey friend, and welcome back to the channel. Today is the second machine learning end-to-end project. We're going to tackle a house in regression machine learning project where we're going to go from scratch, from getting the data into deploying a model that is usable in the cloud. And this one is basically me walking you through the project from A to Z. I'm going to share with you the code. I'm going to share with you the tools, all the resources. We're going to even go through everything, building the UI, testing it, having CI/CD pipeline, Docker containers, deploying into AWS, a lot of analytics, a lot of cleaning. So you're gonna learn a lot of things in this video. So if this sounds good to you, give this video a like and consider subscribing to the channel. I'm doing more and more machine learning end-to-end projects, and the goal is for you to bridge the gap between just working on notebooks into deploying something that anyone can use and benefit from. And that's the whole point of this series. So I hope you enjoy it. And if you have any suggestions, remember to leave them in the comment section and we can try and explore them in the upcoming weeks. So as I mentioned, this is a housing regression machine learning project. We're gonna use a data set from the US about housing in the US between 2012 and 2023. We're gonna find that data set on Kaggle. I'm gonna show you exactly where you can find it. It's good to go through a few prerequisites. There's not much. It's just best for me to mention this initially. So you'll need an IDE where you're gonna code basically. I use VS Code, but you could use PyCharm or Cursor or anything else that you're familiar with. That's no problem. Just choose one you're familiar with. You need to be quite proficient in Python. Everything here will be coded with Python. So a good understanding of it is very helpful. Otherwise, you'll be lost. So that's something to be aware of. The rest is just having a GitHub account, so that you can save your progress in the cloud. And also so you're able just to clone what I'm doing, and it's just good to have GitHub because we're going to use it for the continuous integration as well via GitHub Actions. So a GitHub account is necessary. Then you'll need cloud access. We're going to use AWS. So if you've never used it, it's fine. I'm going to just show you briefly the basics of how you use it. And it's really good to learn how to use AWS because most companies use it anyway. So you're going to gain a skill from it. There's the free tier, which will basically give you $100 in credits. So here I have a free tier as well, and they give you $100, and some services are free to use anyway. So it's good if you can also leverage this so you don't have any costs that come your way. And initially, especially, you need to learn how to optimize your costs and things. So it's best to do it from the free tier. If you've already used it before, ask your brother or sister or someone from the family to create an account and use theirs until you get really familiar with it, and then you can start paying for the services normally. So this one is optional. If you don't want to pay, for example, or if you can't access a free tier for whatever reason, you can just watch me and show you how to do it. But if you're willing to put in $10, $15, if you don't have the free tier, then you can follow along with me as well. And lastly, this is just pure software engineering, data science mindset, which is you're gonna debug a lot, you're gonna encounter many issues, many problems with the code, and that's just up to you to figure it out sometimes, because even though I'm gonna show you things that worked for me, it doesn't mean that it will work out for you 100%. Most things should, but in case something doesn't, you can use ChatGPT or Claude or just search on the internet, and you should be able to find a way to debug things because that's what makes you valuable in the end as a data scientist or as a machine learning engineer. So as I mentioned in this video, we're gonna cover a housing price prediction model. A housing price is a regression machine learning model, and regression is usually when we try to predict a continuous value. So a prediction for housing prices is a value that is continuous, that changes over time, and it's not like a category where we say this house is category A or category B, like if we classify fruits or cars. So this one is a regression problem. And why it's important to understand from the start what kind of machine learning problematic you're solving, because each one will give you a different path to focus on, and each one has different sets of tools and knowledge that you need to be familiar with in order to do things properly. So here is the link to the data set. I'm gonna share with you this resource as well, and you're gonna find them in the link in the description below. Basically, you're just gonna go into Kaggle, and you're gonna see this house TS dataset. and it's basically a 1 GB data set here. You just click on the CSV and you just click on download, and it's gonna download for you. So this is the raw kind of data they're gonna be using. And just to have a quick view here, we can see the date is between 2012 and 2023. The median prices, the median listing, inventory. Basically, there are a lot of different columns, 39, and we're gonna go and explore all this. So first of all, just go and download it, because on GitHub, you will notice that I didn't push the data folder because it's just quite big, and I didn't want to push it to GitHub because GitHub is good to store your code, not good to store your data. So here, the data is not that big, but I avoid putting it in here, so you have to download it yourself. There is also this US Metro data. I'm gonna share with you the link as well, but it's this one here on simplemaps.com/data/US-metros. And this one, you can just click here, the free download, and you're gonna download like a very small CSV file, which is just like 45 kilobytes. So it's very minimal. But this one is useful because in our data set, we have a column that has the regions, and the naming of the regions is a little bit, it's quite a long string of characters, and we're gonna need latitude and longitude so that we're able to do some encoding and things like that. Like you can see here, Atlanta, Sandy Springs, and all these things. It won't make sense right now, but just download them, so later on we're gonna use it. Or when you get there, you just go back and download this. So the project's goal, as I mentioned, is to build a production-ready system with automated pipelines, monitoring, and scalable cloud infrastructure to predict housing prices in the US. And for this, we're gonna go through many very important steps. Let me zoom in here. So first, I'm gonna show you how to set up your environment, how to clone the repository, how to load the data. So this is like the initial phase where we just set up the environment. Then we're gonna go through the data. We're gonna pre-process it. We're gonna do data cleaning. We're gonna do some quality checks. So the way I approach a project like this is initially I'm gonna work in notebooks. I'm more familiar working in notebooks, and what's good is that I can run everything and test everything straight away in notebook cells, and then I'm gonna modularize everything into pipelines. As you can see here, we're gonna have a feature pipeline, training pipeline, inference pipeline. So it will be basically translating everything we've done in notebooks into reproducible scripts. We're gonna do some feature engineering. We're gonna see some really interesting concepts in here. We're gonna do some encoding. We're gonna do some data splitting, which will be done via date instead of randomly, because in a lot of machine learning projects, you'll be just doing random train test splits, which in many cases is good. But since in this data set, we have dates and there is temporal data, which means we have a time series, it's more interesting to use split the data by date, so that the information doesn't leak from previous years and future years between each and every year. So I'm going to show you everything in here. We're going to be using some tools like Great Expectations, which is a library to do data quality checks. We're going to use Optuna to fine-tune our hyperparameters of the machine learning model. We're going to use MLFlow for experiment tracking of our machine learning models, and also saving all sorts of interesting artifacts and metrics from the machine learning models. This basically helps us if we build a few machine learning models, or we have a team of people that are building, we can revert back to previous models, or we can compare models. We can have a champions model, a challenger model, and that's a way for us to always keep improving our models. We're gonna do some Docker container, which will host our application so that it's reproducible. So anyone is able to reproduce from whatever they want. And that's a really valuable skill now in machine learning engineering. And we're gonna use GitHub Actions to run, test, and push our project into AWS, where we're gonna deploy and serve our full application that we're gonna build, using also a FastAPI to give us an HTTP endpoint And as a front end, we're going to create a simple UI app, as I showed you here, using Streamlit, where we're going to, at the end, just choose the year, just choose the month. We can even choose, let's say, a region, and we can just click on show predictions, and it's going to show us the actual price versus the prediction price. And we can see here how good or bad our model performs, basically. Let me just do. So for example, here we can see in the month of May, we have the predictions that are quite off by roughly $22,000 as a mean average error. This is the root mean square error. And this one is just something that I calculated by doing the difference between the actual price and the prediction. So overall, we get 7% error, which is not a bad thing when you think of how many things can affect the prediction of the pricing of a house. So I'm briefly going to mention the technology stack or the tech stack before jumping into the code and showing the code, just so you have an idea of what you're going to be using or what you're going to learn. And as you can see, there's quite a bit that we're using. And in a full end-to-end machine learning project, you will be using even more. So it's good to be familiar with a lot of these tools and why they're even useful in the first place. So if we start here with the data processing, we'll have pandas. So basically for data manipulation. So you can have pandas, you can have polars if the data set's a little bit bigger, or you're going to use PySpark if it's completely big data. So depending on the data size, in this case, we have just less than 1 gigabyte, so pandas is great. If it gets bigger and bigger, then consider other solutions. NumPy for numerical computing, scikit-learn for pre-processing and even machine learning. Great expectations for data quality checks. PyTest for unit tests. This is basically modules to keep testing our pipelines. For machine learning, we're going to be using XGBoost for regression. XGBoost is a machine learning model, and I've done a lot of testing and things, and that was the one that gave me some of the best results and fast as well. So instead of me spending hours here testing models, I'm just going to show you the one that worked. Up to now, it will help us fine-tune our hyperparameters. Hyperparameters is basically what controls your machine learning model, and it can have a huge impact on the performance. So up to now will help us get the best ones so we can improve and tune our model the best way possible. MLFlow for machine learning experiment tracking. So we're going to be tracking experiments. If we keep running, changing the hyperparameters, then we want to save those in MLFlow. We're going to have an API and dashboard. So we're going to use FastAPI to have an HTTP endpoint or REST endpoint. Streamlit to use as our front end for the user interface. And Plotly or Matplotlib, this is just in our notebooks when we're doing exploration and analytics, just so that we see if there's anything that pops or anything that is interesting. And for the infrastructure, we're going to use Docker container for reproducibility. GitHub Actions as our continuous integration and continuous deployment tool. And we're going to use AWS S3 as a storage bucket. ECS, which is the Elastic Container Service to host our application. ECR, which is Elastic Container Registry, if I remember, which will basically have our Docker image. And ALB, which is the application load balancer, which will basically give us access to an HTTP endpoint. So we're going to see all of this, don't worry. I'm just setting the foundations so that we can understand better and better what's happening inside the code. So here we are now in VS Code, and as you can see, we have the whole project here. I will show you how to clone it and how to also access it as well. You see that we have a lot of folders in here and a lot of files. So just to walk you briefly through it, because it can seem daunting initially, you're going to have a README, and README is where I put a lot of information about what's going on. So you can always go back to it and just have a look on what's going on. You also have a Claude.md, which I think they're quite similar overall. But this one is just basically Claude creating for me this resource where I can just have access to what I have done in the project. So we're going to go through important parts. It's data. Data is the raw data that we have, and then the processing and the predictions in here. So all the data sets live inside the data folder. The notebooks is where we have all the notebooks that we worked on, from data splits, the cleaning, the machine learning models, the hyperparameter tuning. And as I told you, I prefer working in notebooks initially because I can go and run whatever I want to run and test it straight away, which is very interesting. And then I will go into SRC, where I'm going to have the Python modules that will basically emulate what I did in the notebook inside Python scripts, because it's more modularized. It's easier to update if there's anything that changes. And it's also the best way to work on this machine learning end-to-end projects, because notebooks can be a little bit clunky and a little bit complex to run, especially when you try to automate. We have tests, so we're going to be testing the features pipeline, the inference pipeline, the training pipeline. We're going to have data quality, as I mentioned, with this library, Great Expectations. So now I'm just showing you an overview. So we're going to go through things. Yeah, we have the ML runs, which is basically the machine learning runs with MLFlow. We're going to see everything that is saved, like the artifacts, the metrics, and so on. We're going to have the models. The models, this .pkl is .pickle, is the models that are saved and that are going to be used by our app. We're going to have the app.py, which is basically giving us access to the application via an HTTP endpoint. And this is where we've built our app in here with Streamlit, as you can see at the top. We're going to have also the FastAPI that we're going to be using in here in a script called main.py. We have the Docker file. This is where we built our Docker image. We're going to have two, one for the main project and one specific to our Streamlit front end app. We're going to have the PyProject.toml. This is where we have all the libraries. And there is also a few other things like the continuous integration. We're going to go through all of these things. So first, let me show you how to set it up like this so you have access to it on your computer. First, just go to the GitHub repository and give it a star. Then you go in here into code and you just save or copy this URL in here. This will help us clone the repository. Then you can go to VS Code. In this case, we can open a terminal like this just by clicking on this button at the top in here. It will open the terminal for us. We can simply just write git clone and we just put the URL in between brackets and we just run it and it's gonna clone the repository. You can see here that nothing really happened when you click on this, but if you just click on open folder, you're gonna find that the first one at the top is the one that we are looking for. It's this one, regression, machine learning end-to-end, and it was just added right now. So basically that's the one. And here you are, you have the project exactly as it was in GitHub. The folder that is missing here is the data folder, but that's something that I show you how to download it. So now that you have it in here, you will need to set an environment for it. And the way you do it is usually you would do UV init, but in this case, it's already initialized because the project is already here. So UV is just a way to download and manage the libraries and packages. So before we used to do pip install C1, for example, but now we can instead, I am using UV, which is faster. You can do UV add C1, for example. So now we're gonna need to install a Python environment for this. So we can just bring one. You choose the one that suits you, but this is the one I worked with. You can do UV Python install 3.11. You can pin it as well, which is optional, but I usually do, just to pin the version. Then I can go and add some dependencies or libraries. The thing is here, we already have them in the project, but I'm just showing you how to do it. We can just still run it. It's gonna run them, as you can see. It did run all the packages. And now that we've done this, we can clearly just go and source and we can just activate the virtual environment. So we're gonna just run it in here And you can see here we're inside housing regression MLE environments. And even if we go, let's say, to a notebook, and we're going to see here at the top right, select kernel, and we can do Python environment, and it's going to give us this one, the first one at the top. And we're going to choose it, and when we choose it, we can see that we are able to run the libraries because they exist in our virtual environment. So now they're going to run. Okay, it's taking a few seconds because it's just starting out, but it should be all fine and working. Now that you know how to access the project, you will need to bring the data because, for example, this, you don't have it yet. So you'll have to go, as I mentioned earlier, to Kaggle. I'll share the link in the description. And you need to go and download the CSV file house ts and just click download. I changed the name of it. I've put it as, this one, I put it as untouched raw original CSV because we're gonna do some changes. You could do the same. So what you could do is go to the project folder. So if you go to the project folder, you're gonna find your project folder here. We don't have the folder called data, so you can literally just create it, just name it data. Inside of it, you can have two other folders. You can call one raw and one processed. So you have the same as I do. And then you can literally just go and put in the two CSV files that I mentioned to you. So it's the US Metro, put them in the row. So one is the US Metro and one is the house dataset. So again, just to show you, the house dataset from Kaggle and the US Metro, you're gonna get it from here and you just go to the free download in here. That one is gonna be needed and I will show you where exactly. So when you have them and you put them, now you should have this data folder and you're gonna have these two row CSVs. And one thing that I want you to be careful about is that the path in here is the path that I used myself in my computer. So you'll need to do a click here and you go to copy path and you're gonna change the path so that it works for you. And now that I changed it, because this is another folder, if I run this and I run this, then I should have the updated dataset. Otherwise, it wouldn't work. And you will have to do the same when we work and we go along every kind of path that you see. Just know that you will need to update the path. So for example, this one, we're gonna save the trained data and the evaluation data and holdout data into this path. So you're gonna need to go and update the path. So that's something to be aware of when working with the notebooks and even with the scripts, because that's something that you're gonna get an error for if you don't do it. So all the paths, just make sure that you remember this and you change them based on whatever you name your files and the path where they come from. You'll see here that we have these could not be resolved. And this is just because the kernel is not selected by default and we have to do it. And now it just looks good. So I'm gonna just close this VS Code. I just showed you how to clone it, how to create the Python environment, how to access everything. But I'm gonna show you from my project because that's from where I run everything and that's from where I deployed everything. Guys, if you're enjoying the video, just remember to give it a like and subscribe to the channel. It does help me massively make videos like this that are quite extensive and complicated. This project took me 3 weeks working on the side. So I hope you find value from it. You're learning a few tips. The best way to learn is by building, and that's what I'm doing myself. I'm trying to go from being a data scientist into a machine learning engineer. So a lot of technical things, a lot of engineering, a lot of reading as well. So I hope that whatever I learn and I share with you, you can benefit from it. And the best way to support me is always to just like it, comment, and just give a little bit of encouragement. Thank you for doing it. And we can jump into the project now. So now that I'm back on my project in here, I'll zoom in a little bit. I'm just gonna go inside my environment. So source and activate the environment. Now I am inside of it. So every time you're back on the project, just remember to do it so that you have access to your environment that has all the libraries and everything installed. So we're gonna start with the notebooks. And we're gonna go and read the data and try to see what we get from it. So we're gonna just create this data frame that has the raw untouched data, the one that you downloaded from Kaggle. This is just so that we are able to see all the columns and all the rows with no problem, so it's not truncated. We can see that this data set has, let me just zoom in even more. This data set has 39 columns and has over 800k rows. And now we're just showing the first two rows. We can see the date column, the median list price, and a lot of other different columns like inventory, new listings. We can also see the zip code, the city, the year, the bank, bus, a lot of stuff, total population, median age. And this one that matters to us is the price and also the city. So we know the price, we know the date, we know the city, school enrollment, a lot of stuff. So we're gonna be working on this. So if we look at just how many years we have available, we can see that the minimum is 2012 and the maximum is 2023. So this data set has 11 years of data, which is great. And we can see that each year roughly has 74,000 rows, apart from 2012 that has less. So this is a good indication for us to know what's the time range of the data. And also knowing that we have a lot of samples. It's not a small data set. There is quite a bit to work with. So there is something that is interesting to discuss initially, is how do you approach a machine learning project like this in a real world environment. So usually the way you will see most of the projects is there is a data set and you're gonna use 80% of it for training, 20% of it for testing, and that's it. You've used all of it. The thing is, in reality, it's best to also think of a holdout data set. So let's say I have this full data and I can use from 2012 to 2019 to train our model. So this will be used heavily to train the model. The evaluation set or the testing set, we're going to use 2021 and 2020. Both of them, they won't be seen during the training, so we can make our predictions on them and we can use for validation, hyperparameter training. And the holdout set, this is good in practice to leave untouched, so that when we finish training and testing everything, that's the one that we're going to apply our model on. And so that we have something that hasn't been affected at all by our training or anything, so that we don't have any data leakage. And that's a very important topic. And here, there is one thing that many of you might be asking is, why don't you just split the data and you do train test split with scikit-learn and you just allocate maybe 80% for training and 20% for testing? And the answer for this one is, if I can show you a visual, if I can find it. I know the quality is not perfect here, but I'm just trying to show you this is temporal data and this is a random split. So let's say here we have this data set that we're working with now. And instead of splitting by time, we randomly split. What's going to happen is that in those random splits, we're going to have data from any year. We're going to have some data from 2012 or 2023. And what will happen is that the testing data will end up already seeing what happened in the training data. So let's say I want to make predictions on the latest years, but on the testing data, it has already seen what happened in 2023 and 2022 because the split was random. So there is a chance that it will take the data from those years in the training sample. And that is a big data leakage. And you will think that your model is performing well, but when you're going to deploy it, it's going to fail completely and it's going to give you weird results. So one tip is when you work with time series or temporal data, which is related to time basically, split by date. And that's what we did, because if I split between 2012 and 2020, and then I use 2020 onwards for testing, then I'm 100% sure that in my testing, we haven't seen anything from the training. So it's pure. There is no data leakage. There is no information that we took from the training and we gave it to the testing, which makes the model behave better and have a better accuracy. But then the results don't reflect the reality. So that's one thing that I wanted to mention. And I see a lot of people completely neglecting. So we're going to just run the whole notebook. So what we did here, as I said, we just split the data into three. We have the training set, the evaluation set, and the holdout set. The holdout set is, just think of it as it won't be touched at all until we build the model and we build the app. And that's where we're going to use that holdout set, so that our model is applied to something that we haven't seen completely. So this is basically, we just cut off the dates. So the cutoff date for evaluation is 2020. And for the holdout is 2022. Basically, 2012, 2019, all of it is training. Evaluation is these 2 years. And holdout, we keep the latest 2 years. So now that we did that, we can see that the training set has 585,000 rows. The evaluation and the holdout is 2 years each. And you can see that they have less data, which is okay. Then what we do is, when we do all that, we're just going to save them. These are still row, so we're going to be saving them into data row, and they're going to be saved in here. So now you should have these 2 row files, and now we're going to have 3 more, one for training, one for holdout, and one for evaluation, and they're going to go inside this row. Remember to update the path so that it fits what you have. So you're going to just click right here, do copy path, and you're going to get the path to that, and you're going to just bring it in here. And then obviously you're gonna name it, give it a name, train.csv, and it's gonna be saved like that, or eval, and so on. So now that we did this first step, which is very important, the splitting, we go into cleaning. And cleaning is one of those steps that you need to be careful with. Otherwise, you're gonna have a lot of inconsistencies, a lot of weird results, and that's something you have to deal with initially. So in this notebook, we're going to bring those data sets that we had before. We have here the training, we have the evaluation, and here we have the metro as well. So we're going to read them in here. We're going to go and look at the cities. And here, the cities, what we want to do is we want to, instead of encoding them like this, because the problem with the cities is that we have many cities. So we have 30 or 40 different cities, and to encode them is going to be very tricky. And if we do use a just nominal encoding, which basically just assigns a number to it from 1 to 30, it's going to give a bias towards the smaller numbers. You will think of them as being more important. And if we do some target encoding, for example, or one-hot encoding will be creating true, false columns for each and every one of the values, which will create a lot of different columns, which will make it very slow to run. And one way that I found to be interesting is to update the cities with the latitude and longitude and use that, because those are numerical values and they're unique. So for example, for New York, we're going to have a specific latitude and longitude combination, for Los Angeles, another one, and so on. And in order to get these, we need this metro's dataset. That's why I mentioned it. So we're going to go now through it. And we have this city mapping. These were just the ones that didn't match, so I ended up doing them myself. But overall, what we do is here, we just replace the city full, which is these values, with their latitude and longitude equivalent from the data. So basically, instead of having the cities, we're going to have the latitude and the longitude. And these are already numerical values, which means they will be easier for us to use in a machine learning model for predictions. So you're going to see here. And if we have the same city, like you see Pittsburgh, we're gonna always have latitude and longitude. So this is way better than having any other type of encoding because this is more accurate and it will work really well. Next, we're gonna look at duplicates. We just wanna see if there are any duplicates. So we can see here duplicated rows, we have 0. And here duplicated rows excluding date column, we have these. But since sometimes you will find a house in the same area for the same price, nothing has changed, but you just get an updated value of it after a few weeks or after a month. So that's why I also checked regarding the date as well. And then you can simply just delete the duplicate. So in this case, I didn't want to have the same house that is listed for the same price, just the date that changed by a few days or a few weeks. I didn't want those duplicates, I just got rid of them. And they're just 6,000 out of nearly 600,000, so it's not even 1% or barely 1%. So it's nothing much to worry about there. I did that for the training data, and we did that for the evaluation data as well. So it's the same process done for the evaluation. Then something very important is we look at the outliers. So the outliers is basically those values that are unusual. So for example, you usually have a score from 1 to 10, and then you see one that has 85. And you know it's an outlier, something happened there, and you go and investigate. And that's what you have to do even with pricing, because let's say the houses are usually between $100,000 to $10 million. And then you have a house that is 250 million. That's a massive outlier, but it doesn't mean it's impossible. It just means that there's something there, and you decide whether you keep it, remove it, give it a lower weight so it doesn't affect the rest and so on. So based on what we see here, we can see there is maximum when you just look at the median list price, and we look at the describe, so we can see the mean, the standard deviation, minimum, maximum. We can see that there is a maximum of $1 billion, billion, not even million. So clearly there are some outliers. Look at this, this is 1 billion. There is no house that costs 1 billion. And you can see that most of the rest is just within this range. So clearly there are outliers, and these will need to remove them because this is really bad outliers, and they will end up affecting our whole model. So what I did in here is that I just looked at the 99.99%, the top 0.01% of the pricing, just to have a look. And I can see here already 3 popped out with $1 billion. So these clearly need to be removed. And I have a few others here that have $50 million, and then the prices drop into 20 million and so on. So what I did is that I can see them in here properly. The 3 that I have $1 billion and others that have those values, I clearly just excluded them. So this is a good exercise to look for outliers, because they will end up completely damaging your results, and that's something that you need to always do when you do exploration. So what I did is that I just cleaned those outliers. So anything above $19 million, do not include it. Let's keep the data set as clean as possible so that the results are good. Obviously this is a value that I chose, and you can adjust it the way you want. But that's something that you can discuss with your team, look on the internet. And this is the beauty of data analytics, is that you're the one in control. You're the one that chooses what makes more sense, and then you work with it. And now that we've done that, we can see that, okay, we have values that go up to 15, 16 million, but most of them are here below 2 million, I would say. And there are obviously houses that are above, because in the US you have houses for 10, 12 million. That's no surprise, but 1 billion, that doesn't exist. So after the cleaning, we can see better values, nothing exaggerated there. This clean data set, because we removed the duplicates, we did the encoding for the latitude and longitude, and we removed the outliers. So 3 major steps. So the data was cleaned, and this one will be saved in processed. So that's why we created earlier this inside of data. We have this processed here. And in that process, we're gonna save the cleaning training and the cleaning evaluation as well. We're gonna be saving them as well. So you're gonna again go to your path no, don't forget, copy the path and use the path that you have, okay? Because this is my computer, it won't be working for you. Then what I did is a simple exploration here. This is basically just trying to understand better some of the averages per city. We can see here San Francisco is the highest in pricing, then LA, and so on. So just to have a good idea of what's going on, so that when you see the results at the end, you kind of come and compare, and you're like, okay, this kind of makes sense or not. And here also looking at the distribution. So looking at the distribution, we can see that most things are below 15 million, and a good median here is around 2 millions, as we saw earlier. So this is just analytics that you go through. Next, we're gonna do some feature engineering and encoding. So this one will focus more on other columns that need to be encoded as well. And in this case, we're gonna go through, so in this notebook for encoding, again, we're gonna read the cleaned data now. So in every notebook, I'm using the output of the previous notebook, just so that it makes sense. Here we're gonna bring all the cleaning data set. You're gonna see here that I added the holdout as well, which I didn't do in the previous notebook. So that's something that you can go and add yourself. You're gonna apply all the same things into it. Or you can completely just, for now, just remove the holdout and skip it completely. So here, we're basically just reading the 3 data sets that are cleaned. And here we only looking at the dates. This is just a quick confirmation that, okay, things are still correct. Nothing is wrong here. Here, what we want to work on first is the date column. So the date column, if I just go, let's say I take the training. So here, if we look at, for example, the training data sets, we can see that we have the date column. But the date column as it is here is not much usable because, first of all, the format, and second, we could be splitting it in a better way. So the way we can do it is to take the date column and split it into year, quarter, and month. So depending on the level of detail you want, you can even go through weeks, days, and even hours. So it really depends. There are companies like Uber that will go even to the minute and try to analyze what happens within each minute. But in our case, we're just splitting that date column into year, quarter, and month. That's as basic as that. And this one is just, I want to see it at the beginning of the data set. So now I run the whole code. If I do, again, run train.df, we're gonna see now the data is split into year, quarter, and month. And this will be fed into our machine learning model so that we can afterwards also filter by the month and the year in our app. So if I show you, if you look at the app, we're gonna filter by the year and the month and also the region. So that's why I've done this. So now if we keep going, we're gonna see that this was applied to the training, to the evaluation, and also to the holdout. Basically, we just make sure that wherever we make these changes, we make it to all of them. Here, we're not training them or making any machine learning into them. We're just cleaning, exploring, doing some feature engineering. So here, there's a key rule that we're gonna fit the encoders or the transformers on the training only, and then we're gonna apply the mappings to the evaluation. Because if we also fit in the evaluation, then what's going to happen is that we're going to have a data leakage, and it's going to be able to see what happened in the training, which will end up leaking information, which will make it look good, but in the end, that's not what's going to happen in production. So I've added these notes in here just as a good reminder. It says here, evaluation stays a true proxy for unseen future data. The performance you see is realistic for when you deploy the model in the wild. So that's why when you fit only on the training data. So you're gonna see here, what we're gonna do here, the zip code, we're gonna do to it a frequency encoding. So a frequency encoding is one of the ways you can encode the data. So when we talk about encoding, is that we have a categorical column or feature, and then we want to make it numerical. And that's important because in machine learning models, you always need to have numerical values. So if we look at the data, so here we go to zip code, and we can see the values of zip code in here, but we're gonna do a frequency encoding so that we have like a number of appearance, which will give more interest into the ones that appear more frequently in the dataset. So basically the way to doing it, we're gonna just do this mapping in here, where we're gonna do the frequency of appearance of a zip code, and it's gonna create for us this new column called zip code frequency, and we're gonna have the frequency of it. So if we show a few more rows, we're gonna see the frequency in here, and that's the one that we're gonna use in our machine learning model. So this is done in here. We have also a target encoding, and the target encoding is gonna be applied to the city. So the city, let me show you the column city so we can have a look. So here is the column, the city. We have it in here. We've already applied a latitude and a longitude for it, but we can also encode the city as well. So what we do here is basically we're gonna just turn the city full, which is a categorical feature, into numerical. And as you see here, we did the fit and transform into the training, but the evaluation and the holdout, we didn't fit on them, so that we don't have any data that is going from the training into the evaluation or the holdout, so that we don't get any data leakage, and we just see that we encoded that feature. Then we're gonna drop unused columns, and these ones we're gonna just drop the columns, the date, for example, because we ended up updating it to years, quarters, and months. City full because we encoded it, city as well, zip code we encoded it, and median sales price because this one directly correlates with the results. So we just drop it in here to avoid the data leakage, and we drop it from all of them. So this is now done in here. So we're gonna just save all these feature engineered dataset in the processed folder. And here we're gonna see that they're all saved in data processed, and they all are here. So this step here is done. We can see here a quick summary of what we did. Dropped and used columns consistency for both data sets, saved 2 separate outputs. Here we also added the holdout, so it's 3. And here I added some information in here, so we have more nuance. I also went and I looked into multicollinearity, and this one is the purpose of understanding if there are any columns that are very collinear with each other. Either both columns give the same information, which makes it redundant, or there is a column that gives away the output, the pricing straight away. For example, in our data set, we have the price of the housing already. And if I keep that in the data sets, then I'm giving away already the result to the model. So that's something to be aware of. So it's important to do some multicollinearity check. And to do so, you have 2 options. You can do VIF, which is the one that we've done here. And basically, it just gives you this score here. And the higher it is, and the more collinear it is, so you have to be careful with this kind of stuff. But one thing to be aware of is that when you use tree-based models like XGBoost, it usually does well even if there's multicollinearity. And here, this is a correlation matrix where you see if there is high multicollinearity between features in here. So I leave all this in here for you, and you can have a look into it. But I ended up dropping these 2 columns at some point because they had a direct impact on the pricing. So I don't remember which one I did, but we're gonna see further on in the project. Now the fun part is looking at the machine learning models. Initially, it's a good idea to do a baseline model. And this one is basically just doing this dummy regressor, and we're gonna just be looking at the median values of the housing, and that's what we're gonna use as our baseline. And we can see here that the results are really bad. We have the mean average error of over $200,000 and the root mean square error of $400,000 and an R square of minus 0.26. So it's a really bad performance for a baseline, but it's always helpful to start with a baseline because you know what's the worst you can get. And if your machine learning model for some reason does worse than your baseline, then it's not even worth doing that machine learning model, because even the baseline that you can run within seconds does a better job. But in this case, obviously, we're going to get something better. Here, we're going to do a linear regression. We're going to use ridge and lasso as well. So a linear regression for this one is going to perform okay, but it's not going to perform like really, really good. We're going to first bring the training and the evaluation data sets. The target is the price. That's what we're trying to predict. We're going to drop the target from X. So basically X is used for as features, and Y is the target, is the price. So all the features need to be, all of them without the price, which is the target. And what we want to predict is just the target, which is price in this case. We applied a standard scaler so that anything that is not numerical will be scaled into numerical values. And here we do a simple linear regression model. We fit the model into the scaled training, X training, and we're gonna predict all those metrics, which is here the mean average error, the root mean square error, and the R square. And here we see already way better than the baseline. We see that we get an 88.6% accuracy, I'd say, in this model, with an error of $54,000. And if we do want to regularize this linear regression, there are two or three famous methods, which are the ridge regression and the lasso regression. So if you've watched my previous end-to-end project, I've also done this one. This one is for reproducibility. So next time you run the code, it gives you the same results. Otherwise, you know, trees are different and it can output different values. As you can see, after running this, we get a 95.8% and the mean error of 32,000. So it's way better than what we had already in the linear regression. And we're just plotting here the top important features, and we can see the median list price has quite a high importance in the data. So now that we saw that XGBoost is the model that we want to use, we can go into the hyperparameter tuning, because that's also an important step and one that can improve our model. So for this, we're going to be using Optuna. And Optuna is a library that helps us fine-tune our machine learning models. And in this case, we're going to be fine-tuning the XGBoost. We also have here MLFlow, and MLFlow will basically help us track experiments of our machine learning models, and it's going to be saved. It's going to be saved in this ML runs in here. So in ML runs, when you run your model, it's going to be created here inside an ID, and each and every run is going to have its own ID. So what's going to happen is, again, we just bring in our data set, we're splitting into train and evaluation. Our target is price, nothing has changed in here. So here, Optuna, we're gonna give it this function in here that basically takes all the hyperparameters, and we're gonna let it experiment with different values, and then it will tell us, okay, this experiment was the best. And in our case here, we're also going to use MLFlow so that we can track all those runs. If, for example, there's one of them that we're interested in for whatever reason, we can go back to it. So the way we do it, we just do with MLFlow.startRun, and we're going to use our XGBoost regressor and the parameters in here. So we're going to use the parameters in there. We're going to do model.fit xtrain ytrain as we usually do. It's exactly the same things. We're gonna output the metrics that we're looking into. So we call the model, we do model.fit, we make the predictions on the evaluation data, we measure those KPIs, and the thing here is that we want to log and save those KPIs results, and we're going to just log those parameters and log the metrics in here. And we're going to just return the root mean square error because that's the one I decided to return back, but you can return MAE or anything else like that. So we've put the number of trials as 15, so it's gonna run 15 different combinations. And you can see here, we can see the root mean square error, and it shows you the hyperparameters of each and every one that was tried. So these are like tests, and in the end it tells us, okay, the best trial so far is number 1, then here is number 4, and so on. And after the 15th attempt, we're gonna get the best one, and that best one is gonna be saved as the best model that we have. So interesting thing in here is that the more trials you have, and obviously the more tests you can get, and the more you can improve the results. And obviously you can also set different thresholds and boundaries. So that's a lot of testing, exploration, and that's, in our case, we don't want to do too much because we don't want to spend forever running this. Now that we had all the runs, we can see the best hyperparameters, and we can see even the results that it's given us. So after running this, we can see the best parameters that we got after fine-tuning with Optuna, and we can then directly just use them, and we can print the results of our metrics, and we can see here the mean average error is the 31,000, the root mean square error is 70,000, and we can see 96.1% compared to 95.8, which is a slight improvement by doing Optuna. And this in a business context can mean a lot of money and a lot of accuracy, which is usually important for businesses. When we finalize our notebooks, which means we did all the steps of cleaning, exploring, analyzing, model training, all the feature engineering before that, then we did some fine-tuning, all these things, we've done them in the notebooks. And for me, I prefer to do that because I can test and do all the things directly within the notebooks, and I can get results really fast. But then, obviously, if you want to do an end-to-end project, you will need to modularize those notebooks into Python scripts. And the way I like to think of them is I like to split them into 3 distinct pipelines. As you will see here, there is the feature pipeline, the training pipeline, and the inference pipeline. So think of them this way. The feature pipeline is everything that you do initially to prepare your data to be trained. So that includes splitting the data, loading the data, pre-processing and cleaning the data, doing feature engineering and encoding. So this is all goes into a feature pipeline. And a feature pipeline will have a few different Python scripts, and each Python script will serve one of those purposes and one of those things that we've already done in our notebooks. The training pipeline touches on everything related to training the machine learning model, which is to finding the right model, fine-tuning it, finding the right hyperparameters, evaluating that model as well. And the inference pipeline, just think of it as the one that brings all into play and runs everything. So instead of doing it somewhere here, we just do it separately. We start with the feature. Think of the raw data. We'll go through the feature pipeline. All of those transformations will happen there. Then when that data is ready, we can train a machine learning model. And then we can just run the full projects in the inference pipeline. So we're gonna cover these now. Afterwards, we could think of reproducibility, which means that we will create a Docker container. Afterwards, we can also think of the FastAPI to give our app or future app an HTTP endpoint before being deployed to the cloud. And we'll also cover the GitHub Actions, which will help us run, test, and push our project into the cloud. So these are the components that we're going to look into next. I just want you to have always this big picture of where you are and where you're heading to, so things make more sense. We first did all the exploration, cleaning, modeling, everything in notebooks. Now they have to be modularized into pipelines. And then we're going to be building the engineering part, which is the CI/CD pipeline with GitHub Actions, putting the project in a Docker container, using the FastAPI to be able to communicate with the web, and then build a UI or a front end using Streamlit, which is a Python library, so that we're able to play around with our model, as you can see in here, which is a nice and pleasant way of sharing with people, and they can play around with the dates, show the predictions, choose a specific region, and see how good our model predicts or how bad it predicts, and that will help you then just go fine-tune, improve things. So now if we go and focus into our pipeline, so I'm gonna zoom in here. So we worked on our notebooks. Now the goal will be to turn those notebooks into pipelines. And the first one, as I mentioned, is the feature pipeline. So let me open this feature pipeline. Let me close this to not distract you with it. So in the feature pipeline, you're gonna see three main Python files. The first one is loading the data. The second one is pre-process the data. And the last one is feature engineering. So those are exactly the steps that we took anyway in our notebooks. We're just reproducing them and modularizing them. And that's a very valuable skill, because when you want to engineer your project and push it to deployment and do MLOps, it's way better to work with functions and modules instead of notebooks. They become very clunky and they're very difficult to debug and to standardize as well. So this is very good practice, and most people have to do it. You can't really deploy your notebooks because you'll encounter so many issues, and it's a lot more engineering headache. So this is the way to do it. Also, there is a part that we're going to cover after each and every pipeline, which is testing those pipelines. And that's why I have a folder here called tests. And you're going to see that we have a test for each and every part of the pipeline. So every time we finish one pipeline, we're going to test it. And that's really good practice. So let's start with the feature pipeline and loading the data. So since we've done everything in the notebooks, I won't be digging too much into each and every line of the code, but we're going to see the purpose of this. So this one is literally to load and time split the raw data set. So that's what we did initially. We just loaded the data. So you're going to see that we literally just loaded the original untouched raw original file. And then we're going to just split the data by date. That's what we did. We had a training data set, and we had an evaluation data set, and a holdout that we're going to keep for our predictions in the Streamlit dashboard. So that's exactly what we did. We just put it all into a function called load and split the data. And that's all. Then we're going to save. We're going to save those split data sets into the train.csv, evaluation.csv, and holdout.csv. And we're going to send them to here, data/row. So this is the data directory. So this is all we do initially. We load and split the data set by date. We've done this all in the notebook. So this was the first notebook that we have here. Then we go into the pre-processing. And the pre-processing, what we had is we first read all the data sets. We clean them and normalize them, the city names. We mapped the cities to the metros, latitude and longitude. That's why we added the other data set. We dropped duplicates and extreme outliers, and we saved again the cleaning step. So if you remember in the notebooks, each and every time we were adding a step where we transformed the data, we usually saved it so that we were able to reuse it afterwards. So I'm just scrolling in here just to show you. In this step here, we saved the cleaning data and we called it cleaning evaluation and cleaning train. So that's, if you go to here, these words were the ones that we've used. So just to explain to you that we're basically reproducing what we did in the notebooks. Don't think of this as if we are doing something completely different and completely new. We're just translating the notebook logic into Python scripts. And that means using a lot of functions, because functions are reusable anywhere. So basically, when I create a function like this, add date features, which is gonna split our date column into year, quarter, and month. And then it's just gonna position them on the first, second, and third columns on my data set, because the data set is just big. I didn't want them to be at the end. I wanted to see them in my first columns. This is very optional. So then if I want to reuse this function, I could easily reuse this logic just by calling this function. And that's the power of modularizing the logic, is that you can reuse those functions in other places as well. So that's what we did here initially. Then we did a frequency encoding, and this one we did it to calculate how many times that value appears. So this is one type of encoding. Frequency encoding is basically when we have a column, let's say zip code, and zip code, some of them appear 20 times, some of them appear just twice. So it gives that number based on how many times the value appears, as you can see here. And we always, when we do encoding, we only fit on the training data, and then we apply that to the evaluation. We never train on the evaluation, otherwise it's gonna be data leakage, it's gonna see some of the information. That's something to be aware of. So these are the encodings that we did. We did the frequency encoding. We also did the target encoding. Basically, target encoding will just replace the category with the average of the target variable. So this is also one type of encoding. I encourage you to go and have a look around of all the types of encoding, the one-hot encoding, the binary encoding, the target encoding, frequency encoding. There are many, and each one will serve a different purpose. So it's good to be aware of, and just good to keep them in mind. And you can do research along the way. Whenever you need one, you can just pause and think, okay, what would be best in my use case? What would be better to use, and also the more optimized. Some of them might be heavy in terms of columns, like the one-hot encoding. Then we add the date features to each and every one of the data sets. So it's the first function that we did in here. And then we're gonna do the same for the frequency encoding and for the target encoding, and also drop in those columns. So basically we just called all those functions we just built before. And then we're going to just output the feature engineered CSV files, and they're going to again be stored in processed, where we have our data in under data processed, and here we have feature engineered evaluation, holdout, and training. So yes, it might seem long, but this is a really nice way of modularizing things. We just again, as I said, translated what we had in the notebook. But this is such a clean way of working, and you'll see a lot of experienced engineers. That's how they would advise you to work. I'm always adding these prints because I like, when I do testing, to have these prints to give me indication. Otherwise, it'll be just running and it'll just go through, and you'll know that it's working, but you don't know exactly what happened. So that's just optional things to do. Now that we've done feature engineering as well, we finished the feature pipeline section. So we loaded the data and split by date. We did the pre-processing, which are the initial cleaning steps. And then we did feature engineering, which was the encoding, and also here adding date features and these kind of things, and dropping some of the columns. Now that we've finished this feature pipeline, what we could do is we could test it. So here we'll see in the tests folder, we go here into test features, and if we have a look into it, so there is a very nice Python library called PyTest, and this one helps us do some unit testing. This is called unit tests, which means that we're just testing one unit, and in this case it's the feature pipeline. So we're going to be calling our Python script. So this one is the feature pipeline load. So basically source dot, this is just the path. So if we go back in here on the left, so this src, if we go inside of it, we have feature pipeline. And inside of feature pipeline, we have the load, pre-process, and feature engineering. So the way we call it, we do from src dot feature pipeline dot load. And this way we access that Python script. And in that Python script, we can import the function that we've built just before. We're gonna do the exact same for the pre-processing and for feature engineering, and we're gonna import all the functions that we've created, and this way we're able to test the whole feature pipeline in here. So first we're gonna look at the load.py, second, preprocess.py, and third, the feature engineering.py. So the three main modules that we had before. And in order to keep it very simple, because this is just testing, we're gonna have some dummy data and small data, just so that we run the numbers and we see if this goes through all the modules that we've created and everything runs well. So we're just creating this dummy data set with a few values, the date, the price, the zip code, the city full, and then we just applying some of the logic that we did before. Here we just again split the date, training, evaluation, holdout. We're kind of simulating what we have in the real project. We're gonna be doing the same things as we did for the pre-processing, basically just remove the outliers, the duplicates, and we're gonna do some cleaning. And in the feature engineering, we're gonna add the date column, which means we're gonna turn date into year, month, and quarter. We're gonna do the frequency encoding, target encoding, and we're gonna drop the unused columns. And here we're just gonna do an integration test. This will confirm the whole feature pipeline works together. We're basically just putting all those together. And this is a way of doing testing. So we gotta go to our terminal in here. Yeah, so here we do Python path equal dot pytest. This is how we call pytest in this case. And then we're just gonna give the path where our test folder lives. So in our case here, our folder is inside tests, and it's called test features underscore features.py. So that's what we do. Test underscore features. I'm even writing it right. Let's run it and see. And we're gonna see that it's gonna run. And cool, we can see that 9 passed, all went good. And this was a way for us to test it very briefly and easily. Now that we're finished with the feature pipeline, we're gonna go to the training pipeline. And in the training pipeline, we're gonna just work on the machine learning model. So first we're gonna train it, then we're gonna evaluate it, and then we're gonna tune it. So in our train.py, we're gonna be training an XGB regressor, and that's what we did before. So we're gonna be importing the appropriate libraries, NumPy and pandas as usual, NumPy for everything numerical, statistical, and matrices, pandas for tabular data, basically. JobLib is for the machine learning models, and the scikit-learn is to get all the metrics we need, and XGBoost is because we're using this model in here. So we're gonna just be reading the default path in there, and here it's the same as we usually do. We're gonna just read the data sets, the training and evaluation. We're not including the holdout because the purpose of the holdout is to not use it in our project in here, and we're gonna apply everything on it when everything is tested and verified. So first, we're defining our target, which is the price. That's the thing that we wanna predict. And here we're just dropping the target from X. X will have all the features and Y will have the target. Basic machine learning stuff that we do. We've here assigned some hyperparameters. Here are some of the hyperparameters that we have in XGBoost. 500 estimators, depth 6, subsamples we have 0.8, and so on. So we're gonna go into here, model equal XGBoost regressor, and it's gonna take the parameters that we've defined in here, and then we're gonna fit the model and make predictions on the evaluation dataset. So then we're gonna just get the main metrics that we're looking for. So the mean average error, the root mean square error, and the R square. We're gonna get them in here and we're just gonna print them. So here we're gonna get already our model. If we just run it, it's gonna run and get us the results. Or in the evaluation as well, we can evaluate and get those metrics. I just run the model here by clicking on this play button, and we got here these results. The model trained, saved to xgbmodel.pkl. So this one, if we go to here, models, we're gonna see xgboost underscore model.pkl. So this is the base model, and we can see here the metrics, and that's what we printed in here, this exactly. So now if we go into the evaluation, if we go back into our SRC training pipeline, in here we go to the evaluation, and all the evaluation does is literally just rerun the same model that we've had. It's going to take the model path from the one that we've run before. So it's basically the trained machine learning model that we just did. It's going to just take it and give us the results of those metrics that we're looking for. So this step is a little bit redundant, but imagine you've had many models and you want to look into some specific ones. So you can just run them in the script and just get the results for it. And here you are, you can see the evaluation, and we got the same metrics here as we did with the one before. So nothing really changed. But as I said, if we had many and we want to test one specific one, here in the models we have these two, the XGB model and the XGB best model. This one will come out from fine-tuning with Optuna. But imagine we had 1, 2, 3, 4, or maybe different types of machine learning models. It'll be nice to have an evaluation script just to do the evaluation very quickly. Next, we're going to go into tuning. And as we did before, we tuned with Optuna. So Optuna will help us just test a few different combinations of hyperparameters and give us the best one based on the number of attempts that we're given it. And MLFlow will basically just store those results for us to be able to afterwards go back and check which models performed the best, which metrics were better or worse, so that over time we know if we want to revert back to a previous model or if we want to have a new model that will challenge the existing model, etc. So MLFlow, it's all about machine learning models experimentation. And the rest is literally the same. So we just bring in the feature engineered data, and then we go through the same process of having our target column. We just read in the training and the evaluation data. Here we're going to give the name, the experiment name, XGBoost Optuna housing, so we can see it on MLFlow. The number of trials, we're going to do 15. So each trial is going to run the full model with different sets of hyperparameters. And if you see in here, what we do basically is, for example, the number of estimators, we give it like a range as we saw in the notebooks. So it's going to go from 200 to 800. So Optuna will be trying it for us and give us the best based on these runs. It doesn't mean it's the maximum best, but based on the runs and the combinations it's going to try. And there's obviously an algorithm behind it that does it in a very structured and intelligent way. So if you want to dig more into Optuna and understand how it is, you'll find many cool resources on the internet to do so. So MLFlow, as I said, will be tracking some of the metrics. And in our case, MLFlow, here we can see MLFlow start run. And here we want to save the model parameters. We want to save the metrics. And it's going to save a bunch of cool stuff. So if we look at it, we could even run it. So now that we started to run it, we can see here that we have this trial number 0, trial number 1, and as we mentioned, we have 15 trials. And you can see here that it's trying different sets of parameters. So if we zoom in a little bit more, this is too big, it becomes confusing. So we can see here, these are random parameters, 528 estimators, 9 in max depth, and so on. And then we can see that one of the metrics is the one that is printed every time. So we're optimizing on one of those metrics. And in our case, which one was it? We chose to focus on, root mean square error. So that's the one that will give us if the model performed better than the others. So here it's going to keep going through the trials, and in the end it's going to tell us which trial was the best, and it will save those hyperparameters as the best model to use, and it's going to be saved as XGB best model. So here we just finished, and it says here best model saved to XGB underscore best model. And here we can see that the best one had 67,955 root mean square error, 31,000 mean average error. an R-square of 96.4%. So this was the best model, and this one's the one that was saved in, where is it? Models, XGB best model in here. So if we go to MLFlow UI, so you just type MLFlow, let me make this, let me move my face, so MLFlow UI, as you can see just in here, and we just enter. It gives us access to this here, this HTTP URL. We just go to it, and here we can see XGBoost Optuna, the one that we named it that way. We click on it, and we're able to see the latest model 1 minute ago. So if we click on it, we're going to see the experiment ID. This one you're going to find it in your project root as well, and the run ID. This is interesting at some point if you want to link it back or something. And we can see here the values of each and every one of the metrics that we saved. And you can see all the hyperparameters here that made us have these results. So if you want to revert back to this, you just know that you need to use this set of hyperparameters. So it's a very interesting way to keep track of all the machine learning models, especially you work within a team. Everyone tried the model. At some point, there was a model that performed better or worse, and you want to keep track of what's going on in the first place. So now that we've done the training pipeline here, so we've done the training, tuning, and evaluation, we're going to again go and test it. It's a good practice to do unit tests. We're going to go to test training. And in test training, as I told you, we're going to be doing a simulation of what we have, because we don't want to put all the data to do testing. So we're going to use a very small model. We're going to use a very small amount of the data, and so that we can just do some tests. So here, obviously, you can't go and just do testing without running the feature pipeline first. And that's why when you build your feature pipeline or your training pipeline, you have to run them first before coming and doing here the testing. So first we just read the feature engineered data set. We need to make sure that we're looking into the same metrics and they are correct in terms of the dictionary. We don't want to have a mismatch. Then the first step will be to train, then to evaluate, and then it will be to tune. So we're exactly just testing on each and everything that we've done before. Here we're going to use small parameters just for the speed. Basically, we're just testing. So just 20 estimators, depth 4, learning 0.1, and sample fraction 0.02. So literally a very small sample. And here we're going to print if the model passed or not. And here we're going to just evaluate on the results of this. We're going to again print if it was passed or not. And then the tuning, we only have 2 trials. We did earlier 15, this one just 2, just for us to get the best results. And we're going to just put it in this temporary path XGB best. This is temporary, so it's not going to be stored at all in our project. So what we can do is we can just go in our terminal and we can just test it with PyTest. So again, we're using PyTest. Yeah, so we're again gonna test this file in here by using this Python path PyTest, and we're gonna just mention the path where the test underscore training lives. And we can see here the test session starts. We can see here that there is some warning, but the 3 main modules passed, but there was 1 warning. So it wasn't an error because it went through, otherwise this dot here will be red, but there is a warning. And here in this case, it just says that there is some file extension deprecated. So yeah, saving the model in UB.json format as default. So it's just a matter of some formatting, but nothing that broke the code. Obviously you can dig into it, but I didn't because it wasn't that important. It was running fine. So it's good to do these testing because you wouldn't even guess this kind of error that maybe, or warning that will maybe break something in the future. So now maybe you're aware of and you take a note. You just say to your team somewhere in your documentation, be aware of UB.json format the file extension that we can use is JSON or UBJ or whatever. So that's something to be aware of. And now that we've done the training pipeline, we're going to go to the inference pipeline, where we're just going to basically just run everything in one go. Because now we've done the feature pipeline where we pre-process and feature engineer the data. We've done the training, which was all about the modeling. And now it's just a matter of running it all in one place. So again, just to remind you, we've done all this in the notebooks, and I spent a little bit more time in them, but I'm still trying to explain to you because in my case, I felt the transition from notebooks into Python scripts very difficult, and I still do. So don't feel intimidated too much by this. Just sit and try to understand slowly. Try to build your first functions. Try to use AI to help you translate your notebook into modules, Python modules, and try to understand what's happening in there. So there is no shame in using AI in your project. I certainly do, but it's good to understand the meaning and the purpose of each and everything. So now we go to the inference pipeline, and here the inference pipeline basically will take the raw data from the stats, apply the pre-processing, feature engineering, and the encoding as well. Then it's going to align the features with the training and return predictions. It is basically going to run everything. And here I just have this little summary that I put for myself, is going from raw data to pre-processing it, to doing feature engineering, aligning the schema, model predictions, and return the predictions, basically. So we have, again, we're going to be using here the pre-processing, the feature engineering. So that's the first part here. We're going to have our default paths. Basically, we're just putting all the paths that were going to be needed initially, because it's easier then to just call them by these variables instead of every time running a path. It's more optimal to do it this way. Here we load the training feature columns, and we make sure that the price is excluded from X, which has all the features, because the price is the target, the one that we're going to be predicting. And here is the core of the inference function. And you're going to see that the core of the inference function, it will have all the steps that we went through from A to Z. So the step number one is to pre-process the raw input. So we're going to be using some of the functions that we've used before: clean and merge, drop duplicates, remove outliers. So these all live in the feature pipeline. Then we're going to do some feature engineering. We're going to take care of the date column using the add date feature. You can see how much heavy lifting we've done before. Now we're literally just calling functions. That's all we're doing. We went through the encoding. We had two: the frequency encoding, how many times that category appeared, and the target encoding. And then we dropped the leakage columns because we had a column that was very highly correlated to the price. We separate actuals if present, so this is just an extra step. We dropped the price column because that's a prediction column. Obviously, we remove it for the sake of doing machine learning. We align the schemas, we load the model, now that we have the model, and we do a prediction on it. And then we just build in the output here. This is just allowing us to run this properly in the CLI. The CLI is the command line interface. It's like your terminal. And this is basically just a way to make it easy for us to just run this pipeline. Now that we looked at inference.py, we can also briefly just go and test it. And here, inference, we can look at it. And we're just gonna basically use, again, PyTest to do some testing on it. Here, we're just gonna load a small sample from cleaning evaluation for inference testing. We're gonna be using here test, inference, runs, and return predictions. We're gonna do a prediction. We're gonna check the output is not empty. We have to include the predicted price because that's the column that is created with our model. And then we just make sure that the prediction is numerical. So here, if we just do testing on inference, we're gonna see that one pass EO went through very cleanly in here. So this is a small test. We can also have a smoke test, and smoke test is more of a bigger version. trying to not just test a unit, but try to test the logic in here. And here, for example, what we did is we took the cleaning dataset. I've done it here in a notebook, so we can run it directly in the cells here. We are just going to take a sample of 5 rows, and we're going to take them randomly. We're going to set the state here to 42, so we get the same exact 5 rows. Here we're just going to print them. So as you can see here, we just print 5 rows, and we're going to apply predictions to it, basically run the inference. So this predict lives in the inference.py, and we're going to see here the results. So let me rerun it. And now that we've run it, we can see that we went through the phase of looking at the latitude, longitude, the drop-in duplicates, removing the prices that were above 19 million. So for this random 5 rows, we didn't have any that were higher. And then we just returned the prediction. So here we can see that the predicted price is this. And usually it would be even interesting to compare it to the price, but that will mean that we'll need to keep the data and show the price at the same time. So now that we've finished the heavy parts of the coding, analytics, machine learning modeling, we will start to focus more on how to make this work for the end user. Basically meaning that we're going to do a lot of engineering and deployment. I'm going to keep things quite simple and straightforward, but I'm going to touch on the most important things in here. So now the data lives in our system. It lives locally on our computer, which means that other people won't be able to access your computer because they just don't have access to it remotely. So what we'll usually do is we'll have our data in a database. So AWS has this service called S3, and where we store our buckets. So we can store here documents, files, and a bunch of things. And in our case, we're going to be storing them here in this housing regression data. So you can do it either go to the console and do it. And I think when you're just starting out, that's a good idea because you build in an intuition of what's inside the platform and the console. And then you can start building on top of it. Remember to, if you're using the root account, it's best to create a user and access from the user. That's the best practice. And here in my case, I'm using this user called Anas in here. You can see I'm on a free tier and I've used already $25 on this because I've been running it for a few weeks. But if you do this project within 2-3 days, it will literally cost you $3-4. And if it's on a free tier, it will cost you like nothing, you know. So if you can do it on a free tier, if you can't do it because you've used the free tier, ask your brothers or sisters or someone from the family to create one, and you can use their free tier. I think that should be fine. Make sure that you're always in the same region that you chose. I am in the London EU West 2. One thing that I would like to also show you, because it's also interesting, is accessing AWS from the command line. So let's do something. I have this terminal here. It's called Warp. I like it because it's visually pleasant, but you can use any type of CLI that you want. You just go and you do AWS configure. Helps you here to continue. And when you do AWS configure, it's going to ask you to input the access key and the secret key and the region and the format. So those you can get them directly in IAM. So if we go in IAM, if we go to the user, click on the user, and then go to security and credentials, and here you're going to see that we have an access key. Let me zoom in more. We're going to see that we have an access key that is already created. It's fine if you see the name because you don't have the secret, but you can create an access key, and those ones, save them somewhere safe because those ones are the ones that you're going to be using to use the CLI. So for example, if I come back in here, I'm going to input these. So let's say you went to AWS and you got your keys and you're just going to input them here. So the access key, the secret key, obviously I'm doing random things, the EU West 2, which is the London one, and here we keep it JSON as it is. So now you did the configuration. If we do now AWS STS get caller identity, this is just to confirm that you have access to the CLI. If you click I should get an error because obviously these tokens don't exist. So I'm going to input my real tokens and I'll get back to it. Now that I put my access keys, I can just run the same AWS SCS get caller identity. And here you can see that it's finding my user in here. And the cool thing here is that now when I'm going to be doing some manipulations in the CLI, if I want to create, delete, or make some changes based on the permissions that I have with the user, I'm going to be able to do it directly from here. So for example, if I run this command in here that gives me all the task definitions inside this house in Streamlit, which I'm going to show you, it's going to go and see all those task definitions. So we can clearly we can make some calls to the console or make even some updates or changes directly via the CLI. A lot of people are more comfortable writing code like this, and sometimes it's much more powerful. And if you want to automate things, this is where it becomes really handy. So I wanted to show you this one because when we want to create an S3 bucket, so I created this notebook here, and in this notebook it's for creating the S3 bucket in AWS, and here we can see the code, and we have here the Boto 3. The Boto 3 is basically how we communicate with AWS. We give the bucket a name because we're going to be creating it directly from our project folder in here. We give it the region. This is very important. Otherwise, you know, it won't be in the region that you want. Then we're just specifying the client, which is S3. It's the name of the service. The region name is the region that we chose. So this is very important. We say the client or the service that we want is S3, and the region is EU West 2, which is a London one. Here is just a helper function. This is upload a file. If not found, it's going to give us file not found. This is just basic troubleshooting, but basically we'll just upload the file from the local path into the bucket directly. And here we can see that the data sets that we want to save are these. Upload file, this is the function. So we want to save the clean data and the feature engineered data for the holdouts, for the train, directly into S3. Why did we skip the evaluation data set? Because now we want to make the predictions and use our model into the holdout data that was completely untouched by using all the training that we've done on the training data. So the evaluation just goes to waste. We've used it to train the model, and the evaluation will be the one that we test on. You would argue that maybe some of this is inefficient. Why is that the case? The data set is from 2012 to 2023, I think. And we took 2012 to 2019 for training, 2020 and 21 for evaluation, and 22, 23 for holdouts. You'd argue that since we're losing that evaluation, 2 years of evaluation, then the holdouts isn't gonna get as good results as what we got in the training. And why that's the case? Because the training stopped in 2019, whilst the holdout started in 2022. So we have a gap of 2 years, and a lot of things can happen in the market that will change the pricing and different factors. So yes, there is a way to optimize things, but this is like a practice project. We try to emulate as close as possible to reality, but it doesn't mean that this is the best way of doing the splits and this kind of processing. So just something to keep in mind, because as a data scientist, machine learning engineer, you're much more than someone that is just writing models. You're also someone to think how you can optimize the whole process. And that's something I just wanted to share with you now. So now that we've got the S3 buckets, if you run this, it should go and create the S3 bucket for us. And if we go and look into the S3 bucket, here, housing regression, we can see that we have the process and we have the data sets that we have here. And we're gonna also have the models, and the models will be also stored in there afterwards. And here, as you can see, we have the 3 files and we have the model. All of them were saved successfully. It took me a little bit of time, so initially just be patient because if the file is big, it might take more time. So just to go back to the whole workflow, now that we've set the pipelines and we are starting to talk about the deployment, we went into AWS. We just set the account very quickly, IAM permissions, the S3 buckets that we created directly from our project by connecting to the AWS CLI first to get the access keys, which is very important. Otherwise, you wouldn't be able to just write from your code to AWS. You won't recognize how to get there. So it's like you're giving it the right to go and do things, which means that you will always need to have permissions that will allow you to do things. So if I go back and just show you, if we go to the user, if we go to IAM, which is the identity and access management, we go to the user, we click on the user, and then we go into the permissions that the user has. We can see here that the user has these permissions that I've given to it, and each user can have up to 10. So here I'm giving it S3 full access. So if you work within a team, they won't give you full access. They will give you read or write, or read and write for certain things that you need. And that's why I think AWS limits each user to only have 10 permissions, so that you don't end up giving a user too many permissions, which doesn't make sense. A data scientist will need a set of services, whilst someone in the sales will need something else. They won't need to access SageMaker, for example. So that's just to show you the S3 and the permissions. Now we're going to focus on the FastAPI. So why we're going to look at the FastAPI before Docker? Because it's just good practice to build the FastAPI app, get that access to the HTTP endpoint, so that in Docker we can literally call it. And then we're going to use GitHub Actions to push, run, test, and push everything to the cloud. We're going to see all this step by step. So here inside of SRC, we have this API subfolder, and inside of it we have main. And this main is the one that will have the FastAPI code. So the goal here, as I've put at the top, is to create a FastAPI app to serve the trained model into a web service that anyone or any system can call over HTTP. So basically making our model available to be used on the internet. So let me do this here. So it's just clean. We call it FastAPI by just calling it from FastAPI import FastAPI. I've added some comments in here so that it's easier to navigate. Pathlib is just to navigate paths. Boto is just to access the AWS SDK. So basically just be able to do changes from here directly. Here we're calling the inference pipeline. Why we're calling the inference pipeline? Because we want to bring the main model that we've built, and we've done all those previous steps before. Here we have the configuration. In the configuration, we just mentioned the S3 bucket. We gave it a name, the region, and here we're just doing the Boto. We're using the S3 and the region directly. So here we're going to load from S3. So now we're not loading anymore locally from our computer. We're loading the data sets from S3, and that's why we needed to upload them and push them to S3 in the first place. So that's what we're doing in here. That's the function. That's what this function does, and it also avoids re-downloading the same data set every time. Then we're looking at the paths. Initially, we just download the model, then we train the features from S3 if they're not cached. If they are, then we don't have to redo it. And then we just load the expected training features for alignment. This is basically just what we did. The price is removed from X, which usually has the features, and Y will have the price, which is the target feature that will help us make the predictions. And here is where the FastAPI comes into play. So we call it here the app because it's an application. And our application has a front end, which will be the thing that we can see and that we can click on. And it has a back end. So what happens behind the scenes? So if we go to our Streamlit app, this is the front end. This is what you see. This is what the results are. But when you click on a button, what happens is what happens on the back end. That's why we call it the application. It's what happens on the back end. And FastAPI is key to this here. So we can see here, FastAPI, we call the app Housing Regression API. We have always these endpoints, if we can call them. So the first one is the landing endpoint, just to confirm that this works and it's alive. So it's just like a slash, get slash. Let me zoom in a little bit more. Then we have get health. just to check if the model exists and works. It gives us just a message saying, hey, this works. And then we have the endpoint here, predict, and this one literally will use our model. And here, this is if we want to run this on a monthly basis, if we want to split the data on a monthly basis. So this is optional and wasn't really used in this project. Initially, I thought I would split the holdout data per month and emulate like a monthly run. Each month will run maybe every day or something as a batch. But in the end, I didn't do it. I just run everything all at once because I didn't want to burn more resources on AWS. And I thought this project will take me long. So I'd rather just cut short, run everything, and just visualize it and deploy it. And here is the latest predictions. So this one will give us the most recent prediction. So this one, if we want to just bring the most recent prediction, in case we have many and we just want to see the latest one. So here, I've added this one in the end, just so that obviously if the code feels a little bit daunting, you just go back and it gives you a quick refresher. So basically we just did the imports, then we did the configuration setup, and this is everything just to set things up in the first place. And then here we downloaded the model and the artifacts. We then did some inferring of the schema, basically the pricing. The FastAPI app is all those endpoints that we've added into it. So all this, if you just do a very basic FastAPI app, you will need just to get make sure that it's healthy, do some health check if you want, and do the prediction, basically. And the code, basically, it just does some checks and sees if things work and the modules are found or not, basically, and gives us access to be opened on the web. So here, if we want to test the FastAPI, what we can do is we can do UV-corn, which is here, UV-corn, src.api.main. So this is where the path we have, src.api.main. And here we just do app and --reload. So if we do it, it should start the FastAPI here. And if we just go and open this, we can see at the top that we have housing regression API is running. And if we just go here and we do /health, it's gonna tell us what the model that we have, and you can see here status is healthy. So now that we saw that the FastAPI is working and is all running, I left a bunch of comments in here so that it's kind of clear when you go through it. The next step will be to build the Docker container. And Docker, what's the purpose of Docker, is for us to be able to reproduce whatever we have in our environment from anywhere. So when we usually work on a software project, there are usually a lot of issues that come, and those are usually linked to the kind of libraries you've installed, the dependencies, the operating system, and all these things. Sometimes even working with a different Python version breaks everything. And sometimes that's not even something that you would realize. A Python version is something that is, I would say, quite easy to figure out, but sometimes it's something so small and you wouldn't even understand why. It could be just a NumPy version that is not compatible with another library, and it breaks everything for your colleague. So Docker removes all these problematics and helps us put our project into a container, and that container, we're going to put it available somewhere on the internet, which is like repositories, somewhere we're going to keep it, so that when we deploy our app, we can get all the configuration, the library, the environment, all from here. So you're going to see that on the left side, I have this Docker file, and I have this Docker file Streamlit. So why did we split them? In this case, because there are different needs. The app itself, or the project itself, is quite straightforward and needs a very base Docker, whilst the Docker file that we're going to create, or the Docker container that we're going to create for Streamlit, and Streamlit is the front end that we're going to use, this one will have more configuration and a direct link to the API. So I've put some comments in here, and here you can see that having separate Docker files for the UI and the FastAPI avoids mixing UI logic with back-end logic in here. So here we're thinking more of the front end, if you want, and here we're going to be thinking more of the back end, even though we could have done everything in one, but it's a good practice sometimes to have different containers. So when you look at a Docker file or a Docker container, there are a few things that you're always going to find. First, you're going to define what image you're using. And in our case, we're using a Python image, 3.11 Slim. So try to use the same one as me. You're going to set the working directory inside the container. So basically, this is just the work dir. You just set in the working directory. You're going to copy all the dependencies, and this is good so that you can have a better cache in here as well. So the dependencies or the libraries, they live in pyproject.toml. So this is where we have all of our libraries in here. So basically, as I told you, this will help us set the same environment as we have in our computer from anywhere. So as long as we have access to that container or the image of that container, we're able to have the same environment as we have locally. So then we're going to install them using UV. That's what we're using. And again, as a reminder, UV is faster. That's why I'm using it. And that's why we have here pyproject.toml, and we don't have requirements.txt. So usually we'll use pip or pip3 if you're using conda, but in my case here I'm using UV, and I highly recommend for you to start using it as well because it's faster and honestly it's very easy to set up as well. Here copy dot space dot basically just means copy everything. It will copy everything that we have, the project files, and then we're going to expose to the FastAPI default port, which here is 8000. It could be different, but as long as you're consistent when you go to AWS and from here as well, then it should be fine. It could be 8080 or it could be different. That's no problem as long as you are consistent. But good practice, I see it's 8000 or 8080 usually. And here we're just going to run it. So here is command to run the API with UVcorn. And UVcorn is just a way for us to run it. We can see UV run, and here we're going to use UVcorn method to do it. And here we just mention where the app lives. And as we saw earlier, the FastAPI app is inside src API main.py. So that's what we have in here. That's our app. And here we're just going to do from anywhere, and port we mentioned 8000. Obviously from anywhere, this is just so that the Docker image is available. But it depends what kind of restrictions you want to have and all that kind of stuff. But this is for the purpose of this project, that's not very important. So now that we've looked at the Docker file for the main project, we can also look at the Docker file for Streamlit. And here, the Docker file for Streamlit, we're also going to have a Python image. Here, I've added this build platform, and this one helps with building across different architectures. What that means is if you're just on MacBook, like myself, and you have two different architectures of MacBook. You have the MacBooks that were built on top of Intel processors, and you have the MacBooks that were built on top of the Mac OS processors, the M1, M2, M3, M4, and I don't know if there's an M5 now. Anyway, so those ones. And that architecture, like in my case here, I had an issue and a bug, and I couldn't figure out what was the issue, and I think I just didn't download the right one for my operating system, and that's just a good thing to add in here. So that's why I added it for this one and not for the other one. We here have just the caching system in here, which is good for us. We're gonna copy and we're gonna install the dependencies as we did for the other one as well. We're gonna copy the entirety of the project as well. Here we're gonna set some environments, some configs. We have the port 8501 for Streamlit, so it's gonna have a unique one as well. The /dashboard is what we're gonna have at the end of our URL to access the dashboard. So earlier we did /health to look at the health of the URL or the model, and here if we do /dashboard, we're gonna get access to our Streamlit dashboard. And just to get an idea, which looks like this, at the top there is /dashboard in here. And here, as you can see, if we want to just run it locally, we can do /predict, and that's how we can get it. And expose to 8501, and this is very important to expose it to the right port. Here, entry point Streamlit, run, we're going to run app.py, and I didn't yet show you the Streamlit code, which we're going to do next, so that you can have an idea. And if we do this, we go to the app.py, and I can show you the Streamlit code. So Streamlit is a Python library to help us build UI, user interface, basically. It's nice, fast, and easy, especially for prototyping. So we call it by doing Streamlit as ST. And here we're going to also use Plotly to have some visuals inside our UI. We're going to get some requests. We're going to use Boto3 to get access to our S3 bucket, and pandas for tabular data. So just to go over it in a simple way, we're going to load the data first. This is the first step. We're going to be loading the data. Then we're going to just ensure that we have the path to access each and every data set. So this is basically our UI. We'll have to use some data. And this is that was just the first step. This is not even Streamlit related. It's just to give it the back end necessary. So Streamlit will start here from caching the data. This is good practice so that we don't have to rerun the prediction on all the folders or all the data sets, sorry, every time. So it's going to keep a cache system or a cache system that will help so that we can avoid runtime and even using more memory and CPU and costs and all that kind of stuff. So here we just, if we can't read it, it will just say, okay, there is an issue, for example, if the length is not the same. So this is just a matter of making sure that the data sets are aligned in terms of length. Here we're also looking at the date, the region, the year, and so on. But now we're going to here be building the UI. And here you do just st.title, and you give it a title. For us, it's housing price prediction, holdout explorer. Then we're going to have some columns. So we're going to be creating like filters where we're going to filter by year, by month, and by region. So this select box are filters, like selection boxes. And if I can show you directly so it makes more sense, it's this select box. So we can see directly in here because that's what we want to see. We also will going to have a button, and this button is the one that is going to run the predictions for us. So let's say we want month 5 and we want to look at, let's say, Chicago, and we're going to show the predictions. Now, when we click, we're going to be running. So not every time that we make a change is going to be changing things for us. And here we got the predictions. We got the metrics that we focus on. This one, the average, is just the difference between the actual and the predicted price. And here we can see nicely how good or bad our model predicted. So the top one here is what we predicted, and the bottom one is the actual pricing as well. So what I did is that I brought, after I did the prediction, I brought the actual prices from the holdout just to see how good or bad we have performed. And we can see here that the model is not that bad, but obviously it could be improved. So some warnings here, for example, if there is no data that is found within the filters. For example, if we have a filter of a city that didn't exist in 2022, but only in 2023, it will tell us no data found, whatever. If there is something missing, in our case, there is none. This one will just write to us that we're running these predictions and so on. So a lot of kind of just debugging steps overall, but the main ones is the ones that we saw, the select box here showcasing the metrics as well as we did. This one I wrote the logic for it, so this one is just comparing the predicted price compared to the actual price to see how far we got from the responses. Here we get a nice subheader for it. Honestly, Streamlit is quite easy and straightforward to use. The more complex you dig into it, and the more you can add complexity, and the slower it gets, and the bigger the data, the slower it gets. So usually people recommend Streamlit for prototyping, but even at my current company, we use Streamlit in production. and it works. It's kind of clunky sometimes, to be fair, but it works. It works really well. So it can be more than just for prototyping. Here we're looking at the regions. We have the options to choose all, or we have the option to choose a specific region as well and make predictions on it. And what I did is I highlighted the selected month. So what I wanted is, I thought if, for example, I just want to look at the month of, for example, here, May, instead of only looking at May, I still want to see the full picture. So what I did, I just highlighted it in red. Yeah, so based on your preferences in this, you can create more or less or visualize differently. But that's the way I decided to showcase it, because I believe that like this, we have a better picture of what happened the whole year for a certain region or all regions. And we can also see the average error that gives us a good indication of how our model performed. Let's say we wanted to look at, let's say, San Antonio, and we want to look at July, for example, 2023. We can see that here we had a higher average error, and if we were only to focus on San Antonio, we could go back and see why this happened, and we look into it. If you're mostly interested in Atlanta, we could look at Atlanta, run it. What's good, you see, it's really fast. It's because the data was cached, and we're not, again, making the whole prediction on all the data, but the data is already available there. We can see that Atlanta is better. And here there is some sort of divergence, which is maybe caused to something, and that's something to go and inspect afterwards. Yeah, so after the highlighting, what I added is the Plotly visual, and the Plotly visual is the one that we see in here. So this is made with Plotly, and I like Plotly because it's quite interactive. You can even zoom in if you prefer, and you can look into things like this. Or you can just hover into things, so it's very pleasant to use. And this is basically just going into what's used in the x-axis, what's used in the y-axis, the labels, giving them names, the labels for the x-axis, the y-axis, the title of the plot as well, gives it the name of the region, or it gives it the name all if no region was specified. This is just that highlighting the month, the way it's done. It's in red, the opacity. So this is like mini details that made that UI or front end the way it is. Obviously, this is not a front end video, so I won't be boring you too much with it. But this is how we create a UI, a very nice UI, usable, that you can share with anyone to play around with this using Streamlit. And Streamlit reads the data from S3. So if the data is constantly updated with new data, new models, then it's going to be directly using those to do all what's necessary. So if we go back to here, Streamlit, the Docker file of Streamlit, we can see that we run app.py. That's the Streamlit app. So we're basically running that code for Streamlit in there. And we're giving it access to the web via this /dashboard in the path so that we can access it. So now that we've created the FastAPI script and we have access, our model has access to an HTTP endpoint, and we've built the Docker containers for the app and for Streamlit, and we also created our AWS account. We set the IAM permissions for the user. We're not using the root. Hopefully we're using the user. Even if using the root is not the end of the world, but it's best practice. We've created the S3 buckets needed where we stored the data sets and the best model so that they can be used within our Streamlit app. Now we're gonna need to somehow run, test, and even push all this into AWS, all these projects. And this is where GitHub Actions come into play. GitHub Actions is a very powerful and very well known and used widely. It's a CI/CD pipeline tool, which is mainly used by DevOps engineers and MLOps engineers as well. And I'm going to show you how simple it is to work with it. So if I go to the GitHub repository of the project, and you're going to be doing from your end, of course. Again, if you remember, just give this one a star. And if you're still watching, just please give this video a like and give a comment, maybe some things they wanted me to cover deeper. or maybe another project. I have something cool coming after this one. I will try to dig more into it, and something that you will enjoy for sure. So here you can see these actions, and in these actions in here is where the CI/CD pipeline will be running. So I didn't show you yet how we set it up, but I'm just showing you where it lives. It lives in here. So when we run the script that we're gonna go through now, it's gonna appear in here and it's gonna be running from here. So if we go back, we go here in our project folder in VS Code, and we can see at the top we have this .github/workflows. It has to be named this way, no other way. And inside of it, we create a .yml file. YAML, it's called YAML. It's like a file structure. It looks a little bit like JSON, but it's different. And this one is the one that is needed when we do CI/CD pipeline. And here I called it CI, continuous integration.yaml. You can call it differently, but the name of the folder and the extension, you have to keep them as they are. So if we look into it, we give it a name, CI/CD pipeline. So you can give it any name you want, but this is the purpose of it, is doing the CI/CD pipeline, which is the continuous integration, continuous deployment. We integrate and we deploy. So here, when do we activate it? When we push changes into GitHub. So as a reminder, if I go down in here and I just do git status, I can see that I have all these small changes that I did and that I haven't yet pushed to GitHub. And this is not a good thing because I should have pushed them. So now what I'm gonna do, since I have many things, I will do git add all by dot it's all. And it's gonna add everything. Now we're gonna do a commit message saying that, for example, updated code structure by adding more comments and details for YouTube video, for example, because that was what I went and I did. Now we committed those, and now that we committed, we're gonna push. So now that we pushed, what did our CI/CD pipeline say? Every time we push, now it's gone. Every time we push on the main branch, here we only have one branch. So if I do git branch, it should only give me the main one. But within a team, you're gonna have many different branches. So this one is specifically when it's pushed on the main. If I go to here, we can see that it started to run. So we'll leave it to run and we go back to it. Now that it's running, we can go in here and we can see what's inside of this code. So we have a few things. We have these jobs. It's what it's going to be run inside of it. Okay, it's run on Ubuntu latest. So this is just the operating system. We're going to be looking at a few things. We have the AWS credentials. This is very important because we have the access key, the secret access key, and the region. And you don't want to hard code them, because if I push this into GitHub, everyone will be able to see my keys and they can go and access and do some things on my behalf, and that's really dangerous. So what you do, you go into GitHub, and on GitHub you go into settings here, and this is really good practice and you have to do it. You go to secrets and variables, actions, and in here you go and you create a new repository secret, and you're gonna be giving them names, and you can store the secrets here and you add them. And every time you do that, you're gonna have all your secrets in one place, and you're gonna just be calling them by this name. And since the CI code is linked to GitHub Actions in here, it's gonna be reading them directly from your GitHub repository. So even you don't have to remember them at all. They live here. They are secure. No one will be able to touch them. So we have the AWS keys, which is the key ID, the secret access key, the region, and the ECR registry and repository. What is the ECR whilst we are on it now? ECR is called the Elastic Container Registry, and it is basically where we're gonna store our Docker containers, because they still lived in our code and our local environment, and they need to live in a repository where they're gonna be stored. And this is where the Elastic Container Registry from AWS come into play. Or you can also store them in the Docker Hub. There's something called Docker Hub. And Docker Hub is basically where you can store all your Docker containers. Now, if we look in here, you're gonna see that some of my other projects, I just saved them in here. and you can go and find your Docker containers and you can store them in here and call them from here. But in our case, we're using AWS, so everything will be in here. And for us to access this, we're gonna need also to have some keys just to be able to access this. Otherwise, there will be no security and anyone will be able to access things on your behalf, which you don't want to. So the first phase was just to configure the AWS credentials. Then we're gonna just log into ECR, which is the Elastic Container Registry, the one we just saw now, basically where we store our Docker containers, just to keep it simple for you. This one will be building, tagging, and pushing those into ECR. So basically, if you think about it, that Docker file that we've built earlier, that we've wrote earlier, we didn't create it. It was just inside the code. So that one needs to be built. It needs to be built. It needs to become real. And in order to do that, you're gonna need to do docker build -t, and you're gonna give it the path that is needed. So this one will be created and saved in our ECR. So we're gonna do it for the first one, which is the housing API, and for the second one, which is the Streamlit, because we had 2 Docker containers. So we're gonna reproduce this and redo it for twice, basically. Initially, when you're working on the project, you do this locally. So you're gonna go to your terminal and do docker build -t docker file, and you're gonna let it run. And you're gonna be debugging it and see what went wrong. And then when it's all good, then you're gonna bring the access keys and all that kind of stuff, and you're gonna push it into ECR or to Docker Hub, depends what you're working on. So now, as I mentioned, we built and push the first container, we build and push the second container, and then we're gonna deploy it to ECS. So now it's time to talk about ECS. So if we think about it, just a moment. In AWS, we set the identity and access management, which is basically giving us the permissions and creating a user that is going to be using the services that it has permission to. Second thing, we created an S3 bucket where we stored our datasets and our best model so that our interface can use them. Third thing is that we created this ECR, Elastic Container Registry, where we store our Docker containers. The Docker containers, they hold and they have all the dependencies, libraries, environments, everything that makes your code run locally will make it run even on the cloud. And then we have ECS. And this is ECS, what is it? It's Elastic Container Service. And in this Elastic Container Service, there are a few things that we need to be aware of. So the first one is creating a cluster, and a cluster is basically what's going to be running those containers. They will make them run and in the cloud live. We have task definitions. Task definition is basically just explaining how to use those containers. So if we go to one, and if we go to the housing one, we're going to see, if we look at the JSON code, we just see the URL, we just see the access value, and we see the port. And that's mostly what we need. We can see the port here, 8501, and some extra information. If we go to the other one, if we go back to the task definition for the housing API, it's going to be on the port 8000. So it's basically just showing from where to access each and everything. And if we go to the service itself, we're going to again have 2 services because we're running 2 containers separately. So we're going to have the main service that is going to be running that task that we worked on, and we can see here that it's running, which means that right now the app is running. We can see here it's healthy. So what you do is, let's say we go back to a cluster, and you're going to create a cluster. You're going to give it a name. You have 2 main infrastructure options. The first one is use it serverless, which means that you won't be running any servers. AWS will do it for you. When it runs, you pay for it. When you stop it, there is nothing. And in the Amazon EC2 instances, is you choose the size of the instances and the servers and their capacities and how to scale them in or out, depending if you need more workload, less workload, is it on a schedule? There's a lot of things. In our case, we're using this one, Fargate. So if you want to go create your own, you just go create your cluster, give it the Fargate one, and you just create. When you do it, you're gonna have your cluster like this with no service at the bottom. And then you're gonna come and create a service. So in this service, you will need to first go to this task definition, create a task definition, give it access to the port, and from here you're gonna just be able to call it. And then when you call it, you can come in here and just do the desired tasks. You have to put it minimum at 1, because if it's 0, it won't be running nothing because it has 0 tasks to run. So if you have 1 task, just put it 1, and this health check grace period, just give it a few seconds, maybe 20 or 30, so it has time to run things properly. So I won't be going too much into the architecture because this is something that you need to figure out. You just need to know the services, and you're gonna play around with them, and then you're gonna start mastering this thing slowly. One other thing that is very important to mention here is that we haven't spoken about how to have access to a URL that will have our project. So if we go to EC2, EC2 is our Elastic Compute Cloud. This is where we have our servers, but we're gonna go to this section specifically, and it's called the load balancers. So in this load balancers, we need to set up this load balancer. It's called an application load balancer. And this one is basically what's going to give us access to our project on the internet. So this is the URL that we're using in order to run our app. So this is exactly the URL. So a few things that we need to be aware of here. We have the listeners rules. This is basically giving the ability to access the information within the project. But we do have this. And if we look into those listeners, we can see in here, if we click on it, we can see that we have a few rules in here. So for example, here, the path to access the prediction, the health, and also to access the dashboard. This one is for the Streamlit part of it, so that we can access our UI interface. So if we go back, the most important here to remember is that we have a VPC. It's a virtual private cloud access. You can find one by default. It will have a few subnets, and there's also these subnets that we can see them here as availability zones. And why is this important? It's because if one fails, if one server fails, we can back to another one and it will still keep running. So there's other ways to ensure that even if the complete data center breaks for some reason, we're still able to run it in a completely other data set, either in another region completely, or here in this case it's just EU West 2A or 2B. So it's just in the same data center, but maybe not the same server or something like that. This is just to ensure that we have things constantly working. So there are target groups as well, and target groups in here, if we look into it, this helps us just to know if the whole connection is healthy or not. I spent a lot of time troubleshooting and debugging this. I've got a lot of unhealthy. Sometimes it's just a matter of the subnets are not well configured, or the HTTP port in the task definition is not well configured. So these are things that you'll need to practice and go through in order to make this work. So usually you need someone that is quite familiar with the platform and a lot of trial and error. So when all these things are done, so just to go through all the services very briefly with you again, in IAM is where we created the user and we gave that user permissions to use certain services, either as an admin or read or write. So that's something that you need to define. We're using a user in here instead of the root account, which is the one that you get when you just start. The S3 bucket is where we store the data sets and the best models that we used. The ECR is where we store our containers, which are the Docker containers, basically. The ECS is the Elastic Container Service, which will basically run those containers. We'll need to create task definitions for each and every one of those containers, which will explain how to access and how to link the container to this service in here via the port 8000, via this image path, they're going to get from the ECR, for example, this one, and then you create a cluster, and within the cluster you create a service. So since we have two Dockers containers, we have two different services, two different container registry, two different task definition. So that's why the work is kind of doubled, but it's literally the same thing. It's just that the accesses and the paths that we're giving them are slightly different. That's all there is to it. And when this service, if you go in here, updates, and for example, this service here, if I had desired task equals 0, this will just switch off the instance and it will stop running and it will stop being available on the internet. But as soon as I switch it to 1, it's up and running again. So when I finish the video, for example, I will turn them both into 0 and I will just, it will just stop it. So I don't have to keep paying much for it. So there's a little cost for each and everything. The storage, the container, some things are very minimal, some things are free. But running the ECS Fargate is the one that costs a little bit the most. So I just make sure that I stop them running. And then when I finish the project, I can just stop everything, remove some of the data and everything. So I'm not charged at all. So be aware that when you finish with this, either stop the project on AWS and delete things, or if you want to keep running it because you're going to write something about it or something, stop the ECS services from working. And then when you come back, turn them on and wait 2 minutes and it should be available. And in the end, when everything goes well, you should get your project in here in a very nice UI, something you can brag about, show to people, show that you took data from housing that was quite a large data set with nearly 1 million rows, and you've done a lot of cleaning, pre-processing, encoding, trained the model, used Optuna for fine-tuning the hyperparameters, MLFlow to track all the experiments, FastAPI to get an HTTP endpoint, Docker containers to make this project reproducible, GitHub Actions to run, test, and deploy your model and your project into the cloud, and AWS to give this life and run them all in the cloud, and Streamlit to build this beautiful UI in here. So you can see that there's a lot that goes into this, and this video took hours, and I didn't even sit and write with you the code line by line. And I believe nowadays writing the code line by line is not the most efficient way to teach online, because you won't be sitting and writing with me line with line, because there's a lot of debugging, there's a lot of things that break. The video might take 20 hours instead of 2 hours. It took me 3-4 weeks to do all these things, part-time of course. But I'm just glad that we sat here and we went through this. And if you're still watching this, kudos to you, honestly. It's not easy, and I hope I explained it the best I could. There's a lot that goes in here. Maybe I missed something, but you have access to everything on GitHub. You can clone the project. You can do all these things. Please, if you've used AWS, I hope you use the free tier. Otherwise, just make sure that you delete what you did, or you stop all the services so that you don't get charged for them. I don't want you to receive a bill and blame me for it. So this is a big disclaimer. When you do this kind of project, just make sure that you have a few dollars on the side that you're willing to spend. Or if not, and you don't have access to the free tier, that's totally fine. I hope you enjoyed watching it with me. This is the second video of this series of machine learning end-to-end projects. There was the first one that I released a month ago about churn prediction, when customers are leaving the company. That was a very interesting one as well, and you're going to see the same concept, so you can reapply things. And the next one will be even more interesting, but that one I'll need to work on it first and then explain it to you guys. So I hope you really enjoyed. Please give this video a like and subscribe to the channel, and I'll see you on the next one.